Hello everyone, it's Dr. Barden here. This video is going to be all about amplitude modulation. This is very related to the last video I just finished recording on ring modulation, in the sense that it is almost exactly the same thing. If you recall from before, ring modulation happens when you are, taking two audio signals and multiplying them together. If we're, talking digitally speaking, we're multiplying them together, combining them in the computer, and the end result is you get two sidebands that are the combination of the two frequencies. So you add them together and subtract them from each other, and that is what the two bands you get. So if you had, if I was just to copy some of this real quick. So if you had some of this, and we had 500 and 400, let's actually, no, we'll leave it there. If I do that and we turn it up, one of those is probably a little more clear than the other, but we're hearing those two combined, 900 hertz, the I can't, I'm bad at singing, I'm going to stop. And then 100 hertz, which is significantly lower before that comes through. So let me try that again at, let's say, 1,000 and 400 hertz. Actually, no, let's say 200. So we're not going to hear 1,000 hertz. We're not going to hear 200 hertz. We're going to hear 1,200 and 800. And that's how we get that unique sound. So by having really high and really low values, you can get some interesting effects. So like if I did 2,000 and 200, well, now it's a lot closer, a lot higher. So you can get a wide variety of sounds. Amplitude modulation is the same thing, except you can hear the original carrier frequency. So in this version here, the 2,000 hertz, that's our carrier frequency, the main sound. And then we are modulating it by 200 hertz, causing us to hear 22 and 1,800 hertz. 200 above and 200 below this original carrier. In amplitude modulation, in this amplitude modulator I have over here, we have our carrier, we have our modulator frequency, but we can hear the side bands and the original sound. So I'll play the sound, and then we will build this one that I have right here. So I'm going to put in the same values as before. Actually, I'll do what I did previously at 1,200, and that can be one high, and we'll set you back to 1,000. So here is the ring modulation again at the 1,200 hertz. Here is the amplitude modulation and a skim, hello, with those same values. So it's different, but it's subtle. So we're hearing, in this case, instead of only 800 and 1,200, we're hearing 800, 1,000, and 1,200 hertz. So you hear the original plus the side bands. This extra stuff over here, compared to on the left of the screen, is what achieves that. It's both a little simple and a little complex at the same time. So in order to maintain the carrier frequency, we have to take our modulator and DC offset it. So we have to take it, and instead of having the values be between -1 and +1, we have to make them all be between 0 and +1. By doing that, the negative values are what was canceling out the original carrier. So by shifting that up, we still get the sidebands and we hear the carrier. So we can get some more unique sounds with just having 3 tones to work with instead. So in this example, again, the way we do that, we don't do anything to the carrier frequency. That meant to select these. That is going to be the same. So we're just going to separate these a little bit. One thing we can do, which I like with this hello skim, that's my computer mouse, with this particular setup, is that we have an option over here that I've labeled as mod depth or volume, and we're effectively just adding a envelope to just the side bands. So you can play around if you want more of that original carrier frequency of, I'll just do 0.1 here instead. That 1000 hertz is very prevalent over the side bands compared to 1.0, where we start hearing the side bands more. So that's what the first part is, and just added a short, simple envelope to that. So I'm going to add that in real quick right here. So we just, simple take a number. I'm just going to steal a float box over here, and we can use line tilde in order to create, not that, and just a simple amplitude envelope, and we don't have to change it over time and have a full ADSR, just basically smoothing out the transitions so we don't get jumps and pops and clicks and things like that. So we can just combine these two, multiply tilde, like so. And instead of connecting here, it's the output of these that comes into here. And just with a simple message, we'll say $1 space 50. This will say move to whatever number comes in from this float box here, move to it over 50 milliseconds. And for the sake of keeping things nice, I'll say 1 period, just to make sure everything knows it's a float. So that's creating the volume control effectively on just the side bands. So if I were to turn this up, we'd get some weird sounds. I think it's kind of fun to play with. So I'll just leave this at 1. Why aren't we... What's happening? Why are you giving me zeros? Does it not like the decimals here? Boop boop, yay, live troubleshooting. I just didn't like 1 for some reason. So it's effectively just a volume on everything. We're not like getting more of the carrier or not, because the multiplication cancels out the carrier. So it's effectively just another volume switch right now, which isn't very useful. So that's where we get this last branch over here where we are offsetting this. So this box right here is saying, hey, do a little bit of math. I'm gonna say, oh, okay, we'll do a little bit of math. Why not? So if I make that, that's the object expr, and we can type in certain things. So we're gonna say 1 period space, and we'll say minus $F1. And I don't want this to be a whole video on the expression object here. Just I'll bring it up briefly because we haven't explicitly dove into it just yet. But we can use it to create math by giving it certain arguments, certain values. Here it can get a little weirdly complicated, but you can set it a lot of different things, and it will provide different operations. So again, we can do a lot of different stuff. This subtracted from 10 is basically what we're doing, but not quite. We can do more complex functions and other numbers and bit operators. A lot of stuff, a lot of math, very powerful. For the sake of this video, we are using this to create that offset here by subtracting the numbers that come in. So that's the short version of what's going on. I'll probably make a dedicated video on the expression object in a future point, but it's a little outside of the scope of what we want to do. So I've got our mod depth right here, and that's going to get our math happening to it. And if we wanted to see what that was, we can see that at 0.9, we get 0.1. It is 1 minus whatever comes into it. So that's what's happening right there. So we'll take that and we'll basically create another simple envelope. We will steal this, connect them up, and add it into this one, this other modulator signal here. So I'll just plus tilde, and we'll just add this one and this one and go, nope, here. So by combining all of these, our end result is we have a frequency and a general envelope and scaling, and we are taking 1 minus the initial value for that scaling and adding it to that scaled signal. So by removing it and adding it back, it always moves back up and scales it back up towards the positive. We've offset that negative value. The end result in terms of what we hear is we get the carrier present. So again, if I was to take this now and set this at 0.01, basically nothing, we get just 1,000 hertz. Here's 500 hertz. It's basically just a sine wave. As we turn this up, the two side bands become more and more present, and we effectively just get a chord coming out of that note. So that becomes a lot more fun. I like amplitude modulation because it gives you more of the sense of okay, you've got a pitch, and then we are changing and manipulating it that way. Whereas ring modulation, we are melding and combining the sounds together. So I like to do ring modulation because it's super quick and easy to do for some interesting sounds. But I also like amplitude modulation because you just get more complex things by keeping that original middle frequency in there. So let's say I did that and 50 hertz. It's a little extra crunchy because now we're hearing 950, 1,000, and 1050 instead of over here Oh, this is the same one. Instead of if we were to just combine them normally for ring modulation, we would only hear the outer bands, which, I mean, still 100 hertz apart at that range isn't going to be the most pleasant sound, but it is significantly less crunchy than our simple amplitude modulation. And just to illustrate what that sounds like, I will temporarily swap these. And actually, that's not what I wanted to do. I wanted to delete you and connect. So here's just the 1000 and the 50 normally with ring modulation. Again, still not the most pleasant of sounds, but not too bad. If I was to then hop back in with that DC offset, much tighter because there's 3 frequencies in that same range instead of 2. So that's the core differences between ring and amplitude modulation. It's just that the carrier frequency has been DC offset. So there's no negative values. It's all positive, and that makes the carrier not get canceled out as happens in just normal ring modulation. From there. And then with this particular setup, we don't really need this second envelope here. We could just go straight into here and still have amplitude modulation. But I really like being able to control how much of the sidebands we actually hear. So you don't necessarily need it, but it's a nice control to have. So this could be a sound source for your Max project. This could definitely be a fun time for that. Good instrument as well. Just like ring modulation, these don't have to be sine waves. I picked sine waves for the basic demos because it's easy and it's not horrible sounding for forever and ever. But we could connect up any sound source to this, and it's going to be the exact same thing. And I'm going to use the ones over here. Just because they're here. So if I was to, instead of connecting to those 2 frequencies, connect to our sound files and multiply them all together, we're going to, have amplitude modulation of the sound files. May not be the most amazing thing, kind of depends on your sound files, but all the same stuff happens. You get the carrier frequency, so you're still hearing all the original stuff, but you also get the side bands. So as the frequencies are shifting around, the side bands do weird things. As the amplitudes change, again, if any of the sounds volume dips out, the whole output goes away. So as the deduk file, pauses, that's what's causing the sound to go away. And that's what we've got happening there. So again, this can be any sound source, any signal. It doesn't have to be just an oscillator. It can be any audio signal. So again, this is a very fun, very powerful way to create very complex timbres very quickly. Again, you can combine this with amplitude envelopes like we did before. You can combine this with filters as well to really just fine-tune your tone and get some really cool sounds that are fun to interact with. So that's where I'm going to end this video. Next week, we'll talk about frequency modulation, which is, on the basic level, not much more complicated than amplitude modulation, but it is a little more complex, especially as you deep dive into it. It can become incredibly complex, but the big thing about that is that you can get a wide variety of sounds with very few inputs and parameters. So that's a very fun way to create sounds, very classic. So we'll spend a week talking about that. That's all I've got now. So again, if you have any questions, as always, send me an email, stop by my office hours, the drill at this point, and I'll see you next time. Bye.